Guys, welcome back to my channel again today. Today we're gonna talk about weak force. Okay, what is weak force? I'm going to give you general definitions of this. Now, the weak nuclear force, or just the weak force, all weak interaction, underline that, acts inside of individual nucleons. Now, nucleons is protons and protons. Just hold on a minute. I have to give you the correct definition. What are nucleons? Protons and neutrons are nucleons. Together they make up the atomic nucleus. Okay, so now let's come up once again. The weak nuclear force, or just the weak force, or weak interaction, acts inside of individual nucleons, which I've just defined to you, which means that it is even shorter ranged than strong force, which means strong force is a short range thing. Today we are talking about the weak force. We'll talk about strong force after. So let's go on. It is the force that allows protons to turn into neutrons and vice versa through beta decay. In case you don't know what's beta decay, particle decay, for example. Now, in particle physics, or particle decay is the spontaneous process of one unstable subatomic particle transforming into multiple other particles. The particle created in this process, that's the final state, must each be less massive than the original, although the total mass of the system must be conserved. So that's what we call particle decay. So now, sorry guys, I have a problem with the lights. I have to adjust. My light system has a problem. It's going on off and on. So what is an example of a weak force? The weak force, also called the weak nuclear interactions or interaction, is responsible for particle decay. This is the literal change of one type of subatomic particle into another. So for example, a neutrino that strays close to a neutrino can turn the neutrino into a proton, while the neutrino becomes an electron. It's like interchanging. Okay, so you can understand what a weak nuclear force is from those definitions, because when I talk of weak nuclear force, you will understand what that means in future lessons. Now let's go on. For example, a Higgs particle may decay suddenly into two particles of light, photon, as that particle may decay suddenly to a muon and an anti-muon. We're going to talk about muons, but just take it from that for now. Take it that way. So, what does decay mean in physics? These terms are very important when we're going to talk about quarks, antiquarks, and fields. What does decay mean in physics? Radioactive decay is a random process in which a nucleus loses energy by emitting radiation. Radiation is the energy that a nucleus radiates or gives out. This is usually in the form of alpha particles, like helium nuclei, alpha particles. Guys, somebody's just washing outside. Forgive for the noise. So let me repeat, this is usually in the form of alpha particles, helium nuclei, and beta particles, electrons or positrons, all gamma rays, which is high energy photons. The nucleus energy, the nucleus, energy reduces, making it more stable. So that's what decay means. I'm giving definitions of these things so that when we talk about it, you have an idea what I mean when I say decay. So I've told you what neutrons are, nucleons are, just told you now. And let's go on to read further about nucleons, which I told is the proton and neutrons together. In chemistry and physics, a nucleon is a proton or a neutron in the atomic nucleus. In contrast, there are free protons and neutrons which are not considered to be nucleons. Protons have a net positive electrical charge, while neutrons are electrically neutral. These are points I put down, guys, for you in this video to give you deep understanding about subatomic and below, even down to the quarks level, what matter is. Okay, so we are digging deep actually in this video. So nucleons in an atomic nucleus have a net positive charge. So nucleons, which is just the protons and neutrons together, have a positive charge. Okay, so that's it. Now when I talk about the mass, number and atomic mass, underline that, very important. Now the sum of the number of protons and neutrons, into bracket parenthesis nucleons, is the mass number A of an atom. In fact, sometimes this value is called the nucleon number. Differences between mass numbers of the same element identify that element's isotope, which differ only by the number of neutrons they contain. You see, they differ by the number of neutrons they contain, otherwise they are the same. So the electron mass is negligible in this case compared to the masses of protons and neutrons. So atomic mass is the sum of the masses of the nucleons, and nucleons being protons and neutrons together. So that constituted the mass and not electron. Electron mass is negligible. So that's atomic mass. Now let's go to the nuclear composition. Nucleon composition, which is protons and neutrons together. Each nucleon consists of 3 subatomic particles called quarks. Very important there, listen very carefully there. Each nucleon consists of 3 subatomic particles called quarks. A proton consists of 2 up quarks and 1 down quark. And let me pause here. What's a quark? A quark is fundamental units of matter. Okay, fundamental, at the fundamental level, we call that quark. So when I'm saying there are 2 up quark and 1 down quark, I'm talking of the fundamental unit of matter at that level. So I've told you a proton consists of 2 up quarks and 1 down quark. while a neutron is composed of one up quark and two down quarks. So by definition, what up quark and down quark means is because there's no any other way it can be described, so it has just been given these names, up quark and down quark, like falling short of how to describe it. So it just been named two up quark, two down quark, one up quark and two down quark. So that's neutron. Each up quark has an electric charge of, each up quark has an electric charge of, I'm gonna write it. Fortunately today my board is clean. Now each up quark has an electric charge of plus 2/3. While a down quark has a charge of, this is up quark, up quark. My board is always small, I write the age. Maybe let me write it from the beginning so that you can see. So the electric charge of an up quark is plus 2/3, right? It is an up quark. Now and then we have, while a down quark has a charge of 1/3. This is a down quark. Okay, this is an up quark, net charge of positive 2/3. What does this actually mean? It's not a complete, it's like a fraction, it's not 1, it's less than 1. So it's given 2/3 positive net electric charge of plus is positive 2/3. While a down quark, and this is the way maybe it's determined actually, because when you say up quark, it means it's positive. Down quark, it means it's negative in this case. So when you're saying that, let me come again, in nuclear composition, each nucleon consists of 3 subatomic particles called quarks. A proton consists of 2 up quarks. It means it has two of these, and this is proton. Let me write it here, proton. Okay, this proton has this, and then so a proton consists of 12 quarks and 1 down quark. It has also 1 down quark, this one. So, and then while a neutron is composed of 1 up quark, which is this one, and then 2 down quarks, 2 of these. So that's the difference. They both have the same thing but in different quantities. Like when you're taking this, you see the proton has 2 of these and 1 of these, while neutron has 1 of these and 2 of these. So that's how the net electrical charge is determined. Okay, so protons and neutron masses are similar. Okay, it's going down to explain that now. A proton has a mass of, let's give the mass of a proton. I don't mind, I'm going to use my hand to clean this. Now, proton and neutron are similar, they are similar. Now, proton has a mass of 1.6726 times 10 raised to power minus 27 kg. Okay, this is the mass it has. The proton has this mass, or the way all 938.27 MeV by C squared. There's alternative way you can write it. You can write it this way or this way. The neutron mass is, now let's go to the neutron. This is a proton. Let me write it here. It's a proton mass. This is a proton mass. Now the neutron mass, I don't know whether to feel, let me try. The neutron mass has 1.6749 times 10 raised to power minus 27 kg, or 939.57 MeV C squared, which makes it about, I'm going to show you in a minute, 0.13% heavier than a proton. Okay, you can write it down if you want. I'll hold it down for you. I'm gonna copy it. Protons and neutron masses are similar. They are similar. A proton has a mass of 1.6726 times 10 raised to minus 27 kg, or 938.27 MeV / C squared, whereas the neutron mass is 1.6749 times 10 raised to minus 27 kg, or 939.57 MeV / C squared, which makes it about 0.13% heavier than a proton. So you can see the difference here is a weight. So neutron is slightly heavier than a proton, and you can see from the figures I've shown you. Now compare this, compare the first one, this one. Where is that figure? See this, compare this, and then compare this. You can see which is higher than the other. You can see this one is higher than the other one. So neutron weighs heavier than the proton in terms of mass. So okay guys, these details about, we're going deep down so that we understand how these things work as subatomic and even down to the fields. There's something even much less than this, the fields. We are not going to, I talked about the fields, but we're going to talk about it deep. So if you stay tuned, I'm going to talk about nucleon interaction, the nucleus, as the next topic, and then we'll go to alpha particles and beta particles. But now, to give you a rough idea, I'm going to show you this diagram. Here we have the neutron, and we have the anti-neutron here, and then we have this is a weak force, actually, weak force. Yeah, I can't write it, I can't draw it. The video is going to be very long. And then we have something called an electron here. And this thing is, I have told you about this, this is a neutron. This is a proton. So we have the proton here, we have the neutron here. and the proton and neutron makes a nucleon. And we have anti-neutron also, so it's a mixture of everything. I want to tell you more about this in the next topic, so please stay tuned. Like, subscribe to my channel, share, like and comment as we go deep down to subatomic and even the quarks and field level of matter. You know, matter is energy. Okay, I will told you in the previous video, so please see you again. Subscribe to this channel. So bye.